Thank you for giving this opportunity. Particularly, I would like to thank Dr. Shravanti Maiti, who has been very generous with me and said she's very kind. She has talked a lot about me, but I am not worthy of it. But we'll try. So before I start my presentation, I must apologize to all of you because I'm not a morning person, so it's morning in Texas. Generally, I don't wake up before 9. Wake up meaning I wake up, but then I don't operate very well before 9. It's 8 here, and I have a full day today, so I have a lots of meeting and other activities, and therefore I told Shravanti that I may not be able to cover the entire 2 hours. So, but then I would like to share with you my contact information, particularly my email. If you have questions or if you have something else that you want to share with me about time series modeling, then I will be happy to answer your questions over email or via email or any other means. I can have one-to-one Zoom meeting as well. So that offer is on the table. So having said that, let me kind of try to focus on what I am supposed to talk about today. And again, I don't think I'll be able to cover everything that has been listed, but then I'll give you the very basic of variance modeling, essentially talking about how we model volatility, because when we talk about time series data, in a lot of time series data, which are very important, we see volatility, which essentially reflects the risk associated with some of the stuff which are important for our decision-making process in our financial life as well as in our economic life. And therefore, it is important that we recognize it and we try to model it correctly so that we can have some estimate of risk, or we can have some sense of risk. Now, I am assuming that all of you are applied economists or applied social scientists, where you basically try to, more than using these techniques mechanically, you actually try to tell stories. We are storytellers. And in order to tell good stories, of course, you have to be very innovative. You have to be very careful how you tease out interesting stories from the information that is available around us. And that's where these techniques or these methods become very, very important. And again, I always say that we are storytellers in the first place. So our story is important, and then all the methods, techniques, software, computers. Of course, those methods, computers, techniques, they help us to tell a good story. And therefore, we should not forget that we are storytellers. We have to tell stories which are convincing, which are interesting, which are important going forward for policy making, for decision making, for coming up with good strategies for different things that we do in our day-to-day life. So having said that, when it comes to data analysis, and data analysis, essentially these are mostly quantitative data or quantitative information, but by using different techniques, we try to figure out some patterns. We try to figure out some stories, and that's why we use these methods. Now, here in this particular lecture, I will be focusing on variance modeling. And now all of you have an idea or know what variance is, right? So if you take So if you have some observations, and if you take the difference between each and every observation from the mean, and then if you square it and take the average, that is basically the variance technically. And it basically tells you how this data or how one particular thing varies over time in case of the time series data. And if you are using cross-sectional data, in that case, how particular parameter, particular indicator or particular variable varies across different cross-sectional units, right? So here, let me try to do the, okay. So in financial, in finance or in even macroeconomics, uncertainty and risk, they play a very important role. In general, uncertainty and risk, they play an important role in our decision-making process. For example, am I going to take a loan to buy a house? Am I going to put my money in a stock portfolio, or am I going to put my money in a portfolio that includes stocks as well as bonds or other financial assets or financial instruments? So those are the decisions we have to make, or we make all the time. Similarly, when we look at the macroeconomy, the overall economy, then also while making important decisions like whether we are going to make an investment, let's say I have a business. So am I going to make an investment in order to establish a business or to expand my business, right? And in order to do that, I need to know a few things about the future, but future is always uncertain, right? And whenever there is uncertainty, of course, there is risk. Okay, so in economics, when we talk about uncertainty and risk, well, they are related concept, but there are slight differences between uncertainty and risk. In case of uncertainty, these are situations where you don't know either the outcomes or you don't know the probabilities associated with a particular event happening or particular occurrence. In case of risk, you know the probable outcomes, you know their probabilities. So in other words, in a way, risk is measurable, but uncertainty is not. So here, when we talk about volatility modeling or variance modeling, we'll essentially talk about how we can measure some of the risk which we need to consider in making decisions. And again, it doesn't matter whether we are consumers or we are investors, we are business owners. We have to make these decisions which involve future, that means which involve risk. And that's where this volatility measure or variance, volatility is measured by generally variance, becomes very, very important. And again, in time series, you see volatility, all right? So for example, now, for example, almost all across the globe, countries are experiencing high inflation. So high inflation is generally associated with high variability as well. So that means there are a lot of fluctuations in inflation, right? And this inflation variability sometimes comes across different items, and it also comes over time. So if you look at the overall inflation, it also becomes very volatile when it is very high, right? And if you look across different items which are included in the calculation of, let's say, consumer price index or producer price index, those also become very variable, right? Both kind of variability creates some sort of uncertainty and risk, and that obviously affects our decision-making process. And that's why central banks around the world, they try to control inflation, because high inflation meaning variable inflation meaning lot of uncertainty and risk. And whenever there is uncertainty and risk, people are generally hesitant to make good decisions, or they cannot make sound or good economic and financial decision that may lead to detrimental effects on growth. And that's why this is very important that we can appropriately model this volatility or this variance or in variability in inflation or in stock prices or stock returns or oil prices, right? So those are important for our macroeconomic life or for our financial life. So again, as I said, variance is often used to measure volatility. Now, if this variance or volatility is kind of constant, it kind of moves the overtime fluctuations in, let's say, inflation remains within a band over a period of time or over a long period of time, then of course that is a good news, because we probably can capture that variance by using an unconditional variance, right? But that doesn't happen too often, right? Of course, the central banks, if you look at central banks around the world nowadays, most of the central banks, they have adopted this strategy of inflation targeting. That means they target a specific inflation band, right? Let's say from 1 to 3%. That means they try to keep the inflation between this band. If they are successful, that will probably generate volatility or then generate variations, which will be constant over a long period of time. In that case, it would not be very difficult for us to, or volatility or variance will not be a very interesting thing to take into account, because we know what is the range of, or what is the extent of the variation. But that doesn't happen with inflation, although central banks have aimed at inflation targeting or have adopted inflation targeting strategy. There have been times when the inflation, particularly now, inflation has gone over this, or it has exceeded this band, and as a result, that strategy has not been very successful. And that in a market-driven economy or in a market economy, these volatilities, you cannot avoid them. You probably can, through appropriate strategy, you can minimize the extent of volatility, but then you cannot really avoid it because there's so many push and pull factors. There are so many factors that will affect the economy, and that at work all the time, it is very difficult to avoid those volatility. So volatility or these variations, they change over time. If they change, then of course, this unconditional variance, which is essentially take the entire time period and calculate the variance, which is basically the deviation, take the deviation of actual observation from the mean, square it and divide it by the number of time period. That will give you that constant variance or the unconditional variance, and that will not really work. So if this extent of variation changes over time, I'll give you some example. I'll show you some pictures so that you can get a sense. And again, whenever you, because I know that some of you who are present in this lecture, some of you are very experienced, and some of you are probably early career researchers. So my advice to all of you would be, before you use any of those very fancy methods, nowadays there is a temptation, because there are so many softwares, and these are relatively easy to use softwares, user-friendly softwares. Therefore, there is a tendency that you kind of mechanically use those softwares in order to get some results and then publish papers. But if you want to be a good empirical researcher or applied researcher, it is very important that you spend a lot of time with the data. You should be able to test the data. You should be able to fill the data. You should be able to sense the data, right? Before you do anything, even simple regression, right? So you have to have a very good sense of data, so much so that after a while, when you see a lot of data over a period of time, by looking at a particular data set, whether it is a time series data or cross-sectional data, you should be able to tell something important or something interesting about the data. So that's basically what I say is sensing the data or filling the data, right? So, and that's why I'm saying that before you do volatility, before you do regression, arcs, guards, stationarity, you should have a good sense of the data, right? So when I, again, to make this presentation interesting, I'll keep telling you anecdotes. So when I started my doctoral studies and at Southern Methodist University, my advisor has a very good data sense. So he has got, in fact, his research was entirely on macroeconomic. In fact, his early research when he was a graduate student, and he was a student of Robert Gordon. And so his dissertation was on data, macroeconomic data. And therefore he had developed a very good sense of data. So he just look at the data and he can tell you a lot of interesting stuff about the data without doing anything. And that's what you need. And that for that, you need to look at a lot of data, think about it, and see what information you can extract before you do any kind of econometric analysis or before you apply any of the methods that we talk about or we teach in the classroom. So again, here, that's why it is very important that whether it is volatility, whether it is stationarity, whether it is trending properties, it is very important that you look at the data first. Okay, so you plot it and look at it, the data, and try to kind of see, turn it over, look it from the other side, look it from that side, this side. So I mean, there's the different ways, even without using very sophisticated econometric or statistical methods. Okay. Now, before I show you those data, I want to introduce you to this idea of volatility clustering. So generally in macroeconomic data or in financial data, what happens, there will be times when one particular variable, let's say stock prices, becomes very volatile. So it kind of moves up and down too much or to a large extent. And then there will be some tranquility. There will be some period where it doesn't move that much. And then again, there will be a lot of kind of movements or variation in the time series in that variable, meaning the observations that we collect on that variable. Let's say stock prices, or let's say, well, inflation in some countries, yes, but generally in more advanced matured market economies, inflation has not been a problem until last year or until this year. Okay, so for almost 30 years, more than 30 years, these countries experience very low inflation. Of course, in developing countries or emerging market economies, we have seen some volatility or periods of volatility in inflation. Or if you look at exchange rates, right? So now that most countries have a floating exchange rate or some form of floating exchange rate, you see periods of volatility in the exchange rate, and then will be followed by some period of relative tranquility, and then there will be again movement. So this particular phenomenon is known as volatility clustering. Okay, we see that in oil prices, stock prices, portfolio returns, interest rates, exchange rates. And and what are the sources of those volatility clustering? Sometimes they are known, sometimes they are not, right? For example, right now, why we see so much volatility in the stock market, or some of the reasons probably we can guess, and we can guess correctly, but others we cannot, right? So, it is not always possible to see all the different sources of volatility. But then these sources of why we see different patterns of volatility, there are many. There are several sources, or there are several reasons why there could be volatility in this time series data. So here I am showing you, and when I was getting ready for this presentation, I was trying to find some data from India, and I looked at the US dollar and then Indian rupee exchange rate, because lately Indian rupee has depreciated significantly against US dollar. And being an immigrant myself here, the fact that I have family, I go back there. So this is the movements in exchange rate obviously affects a lot of decision that I take in my life, or in my personal life. And therefore I thought that, okay, so if I can find, let me take a look at the exchange rate. So I have collected data on monthly exchange rate. You can actually get daily exchange rate for most of these foreign currencies, but I took it at monthly interval. And so on the left-hand side, you will see that this is just a nominal exchange rate. So Indian rupee for each dollar, $1. And if you look at the left-hand scale, that is, you see 3.2, 3.4, because I have taken the log values, natural log value of the exchange rate, and that's why that is the scale, okay? And so here, as you can see, you will, let me see if I can. Okay, so if you see, there are, of course, first thing that you will notice here is that since 1992, that is immediately after the economic reform of 1991, right? All the way until September 2022. So the exchange rate, the value of dollar in terms of Indian rupee has gone up, right? So if you look at over this 30-year period, then you will see I can draw a line through this, right? So that will probably represent what has happened over this 30-year period, right? But then if you look at the short run, then you will see a lot of movements. For example, around 2006 and 8, there was a drop, right? So it was going up, up, up. Then there was a drop. Then there is some movement around here, but from about 2012, it looks like it is going up with a lot of short-run volatility, right? So you can figure out that there are periods of turbulence, there are periods of volatility, followed by there are periods of tranquility, right? So another way of looking at so what is going on, just take the percentage change month to month, okay? So since I have the natural log values, I will take the first difference, multiply by 100, that will give me the percentage change, and that is what you see here on the right-hand side. So it's the same data set, But what I'm doing here, I'm taking the month-to-month changes in the exchange rate. Okay, so since these are first difference of natural log multiplied by 100, that gives me the percentage change. And that's what I have plotted here. And here again, you will see I have circled some of them, not all of them, but there are other volatility clustering here. So here you see around 96, 95, 96, there were some volatility, followed by some period of not so much movement. And again, around 98, that is immediately after the Asian flu, there was some volatility, and then there was some calm, right? All the way until 2004, 2005, there was some volatility, not to the large extent. But then if you come to 2008, 2009, that is the period of Great Recession or the global financial crisis, there you see a lot of volatility. Okay, then there was some calm, and then 2012, 13, 14, there's a lot of volatility. But after 14, it is relatively calm. And then after that, again, you see some volatility. So that's what is happening with the exchange rate, US dollar and Indian rupee exchange rate, right? Now, if you are somebody who is active in the exchange rate market, or you do a business where you are exporting or importing to outside India, or you are bringing things from outside India, then of course these volatility measures are or this volatility in the exchange rate is important for your decision-making process. So if you are into export and import business, or if you are into investment in foreign financial assets, then of course these exchange rates are very, very important, because you are making decision for next 1 year, 2 years, 5 years, 10 years, depending on your time horizon. And there this volatility or this volatility clustering may be an important thing. And therefore it is important that you try to measure, or you try to model them correctly, so that it is informative when it comes to making decisions. Hopefully so far so good, right? So again, I'm not talking about like modeling yet. I'm just talking about the data in general. So then again, I thought that, okay, so what next? What is the other kind of data that I can look at? Now, whenever I go home, I talk to my friends. Now I see that it is, at least the friends with whom I went to college, they are middle class, and they have good jobs, and they also talk about investment nowadays, putting their money. For example, my father's generation, they were very conservative in the sense that they used to save. They actually had they were very good with finance. But then the way they will put their money, or they will invest, or they will save their money, is putting in a bank account or buying life insurance policies, right? So those are the ways they used to save. But nowadays, when I go and when I talk to my friends who are my generation or my next generations, they talk about putting money in the stock market or in the bond market or in mutual funds. Some of them also do it in cryptocurrency nowadays, right? And then they talk about the rate of returns. And as a result, I thought that, okay, let me take a look at the stock prices, okay? So, and that's when I collected some data from Bombay Stock Exchange, and this is Bombay Stock Exchange Sensex market index. I think there are 50 companies. These are stock prices of 50 different companies, 50 or 30, 50. And so if I take a look at, and they didn't have, I think this is the data that I could find, at least I could find. And so this is, again, daily data from January 2nd to 2012, that is after the Great Recession or the global financial crisis, all the way to September 2022. Again, if I have to draw a trend line, then I can draw a trend line from 2012 to 2022. But if you take a very long view, if you take a very long period of time, obviously the stock prices have increased. Again, I have taken the natural log of the stock price indices. And but then if you look at very short time period, right? So duration, then you see a lot of movements in these stock prices. And these are daily data, and therefore you can see that there is some movement at the daily level, and then but then over a period, short period of time, there are some movements. For example, see here, there are daily movements, but at the same time, there is also this movement, right? And then there is this movement, and there is this movement. So now how do you, this is probably not very easy to see in that particular picture. So I did the same thing that I did it with exchange rate. So what I did, percentage change in daily BSC, Sensex, and index, and then I plot it, okay? So when you do that, it looks something like that, okay? So again, there are volatilities, volatility clustering. So looking at the right-hand side picture or the figure, you can figure out the volatility clustering. So there are periods of very high variations followed by relative calm. So turbulence, tranquility, turbulence, tranquility. So that's the nature of a typical market economy, right? And it shows up in stock market, it shows up in inflation, it shows up in interest rates. So this is about the stock market in India. Okay, so I am hoping that you are getting a sense of what volatility clustering is. And that's what we will try to model using this ArchGarch modeling strategy or methods. Okay, so that's basically the goal. And now you think about, so as I said, we are storytellers. So when we say we are storytellers, so what are the stories that you want to say? There's some very, for example, portfolio returns. So they are, obviously you will observe volatility return, but then there are many other areas where volatility clustering could be an important thing to model. And particularly macroeconomic, there are lots of macroeconomic data where you would like to observe, or you would expect volatility clustering, and you would like to model them appropriately so that they're informative for policymakers or informative for individuals like ourselves. Now, here, the main as a method or as a modeling strategy, we would like to talk about autoregressive conditional heteroskedasticity, okay? You are familiar with the concept of heteroskedasticity, right? Generally in classical linear regression model, which is the first thing that we try to learn in an econometrics 101, right? So in classical linear regression model, we assume that the error term is homoskedastic. That means doesn't matter. Homoskedastic meaning the error term has a constant variance, okay? So it has a constant variance, and that's what homoskedastic mean. Now, here we are talking about heteroskedasticity because variance is not constant, right? Variance will vary. And that is a departure from the classical linear regression model. Now, before the heteroskedasticity part, we have added two additional terms, autoregressive and conditional. So together we call it ARCH. Okay. So now again, thinking about how we learn or what we have learned in basic econometrics, we normally observe heteroskedasticity in cross-sectional data, right? And you would expect heteroskedasticity in cross-sectional data. Let's say you are looking at the relationship between disposable income and consumption, right? In that case, you will expect that the error term probably would be heteroskedastic. And let's say the data set that you are using is a cross-section of households in the state of Bihar, or in the state of Maharashtra, or in the state of West Bengal, or in the state of Assam, right? In that case, you would expect that the error term would be heteroskedastic, right? Because each household, right, will be in the different income levels. So there will be some low income people, middle income people, and high income people, right? So as a result, because of these individual characteristics of each of these households, which we would include in a study like that, right? So you would expect that the variance will not be constant, right? On the other hand, there's another issue, right? So we assume in classical linear regression model that there is no serial correlation in the error term. That means the error in period T does not depend on the error in the previous period, right? So that means there is no serial or autocorrelation. But again, in most time series data, we observe autocorrelation, meaning generally this time period will depend on the previous time period, right? Now here we are talking about time series, but we are also talking about heteroskedasticity, right? So that's what is interesting here, because we are talking about heteroskedasticity, which we normally observe in cross-sectional data. But at the same time, we are tying it with autoregressive part. There is a time series characterization of this heteroskedasticity. And basically, we are combining two things in one particular concept, and that will be used for modeling this volatility clustering. Okay. Now, if there is heteroskedasticity, that means if there is a violation of this very basic assumption of classical linear regression model, what happens? Well, OLS estimate is still unbiased, right? But then the standard errors are so tight that it gives you a false sense of precision. You feel like you are estimating the coefficients very precisely. But that is because of the nature of the error term, or the heteroskedasticity. So how do you correct that? Of course, in again, very basic econometrics textbook or class, you will say that if the heteroskedasticity, the nature of heteroskedasticity is known, then you can use generalized least square, right? So you can transform its variable, and then you can basically re-estimate the model using generalized least square, right? That is one. And then along the way, there were some other discovery or other invention of robust standard errors, right? So where the standard errors are robust to various different forms of heteroskedasticity. So as a result, that false sense of precision kind of goes away, and you are correctly basically estimating the coefficients, and you are also evaluating the statistical significance correctly, right? But for robust standard errors to work, your sample size has to be large enough. In a small sample, that may not work. And now in a small sample, how do you calculate robust standard errors, or what you do in order to avoid or in order to take care of heteroskedasticity is kind of debatable. There are people talk about different ways. Again, I'm not going there. What I am trying to say that the time series which exhibit volatility clustering, they are characterized by generally they are characterized by autocorrelated heteroskedasticity. That means this volatility clustering or this variance, they are not like jump from one particular nature to another. So in period T, it will depend on what happened in period T minus 1. So there is some memory or there's some connection to the previous period. So if it is very volatile, if the stock price is very volatile, let's say in period T, then it would be volatile in time period T plus 1 as well. Well, there will be some difference in the extent maybe, but it cannot be, it generally is not the case that it would there will be no volatility at all. There is some memory, there is some persistence, right? And that is what we call the arch effect, okay? That is called arch effect. It is conditional because it is conditional on the information that is available until the period T minus 1, okay? And that basically creates this autoregressive character of this heteroskedasticity. And that's why we call it autoregressive conditional heteroskedasticity. It is conditional upon the information available up to T minus 1, okay? And so that is called arch effect. Arch effect is basically there is some persistence in this volatility clustering, okay? And this arch and Garch models, arch is basically autoregressive conditional heteroskedasticity, Garch is generalized autoregressive conditional heteroskedasticity. They're designed to deal with this time series heteroskedasticity or its arch effect. And the first paper, this was a contribution of Robert Engel. You know about him. He was awarded the Nobel Prize with Clive Granger for his contribution. This is basically a Nobel Prize winning idea, right? Before that, how people recognize that there are volatility clustering and variance basically does not remain constant. So if you look at short period of time, it changes over time, right? And how did people try to model those? Generally, people used what we call the rolling standard deviation, okay? So rolling standard deviation, meaning take a sample period, within that sample period, take a window. Let's say you have data for 60 years, take a period of, let's say, 3 or 4 years, and then let's say monthly data 4 years, right? Or 5 years. And then you roll that window, right? So you add 1 and then drop 1, add 1, drop 1, add 1, drop 1, and keep calculating or keep estimating the variance. And that will give you a sense how variance changes over time. So that was the way, that is how some researchers or most people used to look at this changing volatility or changing variance over time. But then Robert Engel basically came up with this idea, and he thought that there should be a better way to model this, and that's where his 1982 Econometrica paper, that is the seminal contribution, And he kept writing on those. And after him, another big name in this area is Volatility. Volatility also has contributed significantly to this method, development of this method. Okay. So here is some formalization. So a typical specification would be, so let's say y is the variable that we are trying to analyze. So this is like a standard regression model. So here, by putting this omega t minus 1, that is basically the information set, that is the information available in period t minus 1. And these are x is some regression, and there are a wide range of possibilities. It could be just a trend. It could be the lag values of y, or it could be some exogenous variables. So there are a lot of different possibilities you can include. So it basically can come. So how you specify that this equation depends on a lot of different things, right? So it can come from a structural model. It can be a purely empirical model, or it could be just a univariate analysis, in which case you basically include a bunch of lag values of yt. And then, well, there are ways, as you probably have known, or you have kind of discussed in last few days, how you select all those lag values if there is a persistent series. I mean, it depends on the data generating process. So here we assume that this error term is independently and identically distributed with a mean of 0 and and this is the variance. Okay, so what is different in this variance from the classical linear regression model? Well, in classical linear regression model, it does not have this subscript t. And t essentially tells us that every time period, this variance will be different, right? And so we are basically here introducing a time-varying variance. So it is not constant, right? It changes over time. Now, how do you now model this variance, which does not stay constant, but it changes over time? And that's where this concept of arch effect, the fact that variance has persistence, it basically the value of the variance in period t depends on the value of variance in t minus 1, maybe t minus 2, maybe t minus 3, right? So here, one very simple way to specify this variance is dependent on the 1 period lag values of the error term. Okay. Now, a variance cannot be negative, right? So now if you estimate this model and it turns out that delta 0, which is a constant, and delta 1, they are negative, right? This cannot be negative because this is a squared error, right? And if the delta 0 and delta 1 are such that it gives us a negative value, of course, that cannot happen. And therefore, we have to make an assumption that, that these deltas are positive, or at least non-negative, right? And also, there is another assumptions that we have to make is that this delta 1 is less than 1. Because if it is higher than 1, then of course, this will kind of blow out. This will explode, right? So this variance will get so big, then obviously it will be almost meaningless to try to model it. So these are the two restrictions, and these are very important because many of the developments, later developments, which I think I'll not be able to cover today, but many of the recent developments or later developments of this arch-Garch modeling is because of this particular this particular assumptions, right? So we need to put restrictions on the parameter estimates, and sometimes it become very restrictive, and that could be problematic, and that's why we generally people have come up with different ways to model this arch effect. So now if you take expectations, then from the first equation, you get this, what we call the mean equation. So this is the mean equation. We are taking mean, right? And again, this is conditional mean because this is conditional upon the information available at the time period t-1. And similarly, we can also calculate variance using mathematical expectations. So here, the form of the conditional variance is this, right? Again, coming from the specification I have shown in the previous slide, right? So this is, first of all, the conditional mean. The first equation here is the conditional mean, and this is conditional variance. So these are the two equations, right, that are important, or that we try to estimate using this arch model method or Garch modeling method, okay? More generally, you can extend it. So here in the previous case, we did just arch 1 because we said, or we assumed, that the variance depends on 1 period lag values of the error term, right? So here we can generalize it to p lag. So let's say there is a persistent memory for a longer period of time. It not only depends on the previous period, but it depends on p previous periods, right? So in that case, I can write this. This is the conditional variance equation. Okay, so the mean equation will be the same. Conditional mean equation will be the same. This is the conditional variance equation, and this is what we call the arch P model. So P could be 2, could be 3, could be 4, right? So could be 10. It will be part of the modeling strategy. Now, before we talk about how we estimate this arch model, or how we estimate this mean equation, conditional mean equation, and the conditional variance equation, how do we detect the arch effect? How do we know that there is arch effect? Of course, if you just do what I have shown you, just plot the data and try to see if there is volatility clustering, that will be somewhat informative, right? So, and if you have a good data sense, probably you will suspect something. But sometimes you need very formal ways to make sure that there is volatility clustering, right? And that is where let me talk about a few things that you can do. First of all, let's estimate equation 2. If you remember, what is equation 2? That is basically y is equal to beta 0 plus beta 1. X is a vector, or it could be a single variable, or it could be a vector of different variables. So you estimate using the least square method, okay? And then extract the residuals and square them. and then plot those squared residuals, and that could be indicative of arch effect. Okay, it's a simple exercise. So you use OLS, you estimate that first equation, which is y is a function of x, right? X. Then take the estimated residuals and square them, and then plot them. And that, looking at the pattern, you can see that there might be arch effect. Or more formally, what you can do, calculate the autocorrelation of the squared residuals and use the Leung-Box Q statistics. Okay, and that goes back to probably your you must have done this arch and garch. I'm sorry, the AR-ARMA model, right? So they are one of the ways to kind of figure out what kind of ARMA model you basically look at ACF and PACF, right? Autocorrelation function and the partial autocorrelation function. The pattern kind of are indicative of. So you can do that here too. Or you can look at the Q statistics, which will basically tell you whether there is autocorrelation or not, right? So whether they are serially correlated or not. So here basically is the same thing. So you obtain the estimated residual from the OLS estimate, then estimate the following. So there is another way to do this. So you estimate that model, you extract the estimated residuals, square them, and then you basically regress it on lag values of those estimated residuals. Now, if there are arch or Garch effect, then this delta coefficients should be equal to 0. If there is no arch effect, right? So in this model, right? So let's say there is no arch effect, that means variance is constant, right? In that case, all these deltas should be 0. This is another way of detecting whether there is arch or Garch. Now, so these are some of the ways that you can use in order to figure out whether there is Garch effect or not, or arch or Garch effect or not. Okay, there's something happening here. Okay, so here I am taking that data, the US dollar and INR exchange rate, and I'm using the log values. And what I am doing here, I am fitting a trend. So I'm estimating this model. So that mean equation I was talking about, right? So this is, let's say, the mean equation. But as you looked at the data, there was a deterministic, I mean, you would suspect that there was a trend over the long period of time. So I regress it on a constant and a time trend. So that's how I did it in eViews. I don't use Gretel. So eViews, sometimes I use it, not very regularly. I normally, for my time series stuff, I do RATs. I use RATs. I don't know how many of you use RATs, but that is something I have inherited from my advisor. So I do RATs or MATLAB. So eViews, sometimes I do that. So I cannot claim that I'm an expert in eViews, but this is what eViews has given me. So I regress the natural log of exchange rate on a constant and a trend, right? So this is what I get. So if you look at both, the constant and trend are statistically significant. And after that, what I do, I extract the estimated residuals, and then I take the squared and then I plot them. So this is what the plot of squared residuals. Okay, so when you do that, they look like this. And the fact that there are big spikes, right? So then there are not much variation tells me that it looks like there are arch effects in this exchange rate. Okay, so this is an indicative of, this is not a very formal test, but this is indicative of arch effects. Then I plot the correlogram of the squared residuals. So they look something like that. And these are the autocorrelation numbers. These are partial autocorrelation. And this is the Q statistics. And these are the probabilities associated with them. So here, the maintained hypothesis is that there is no serial correlation, right? So when the probability is very small, that tells me that you can reject that null. That means there is serial correlation, right? So that's how you look at this Q statistics. Now, about the autocorrelation, this pattern seems to suggest that it is an AR1 process. That means the variance should have, because I am looking at the autocorrelation of the squared residuals, right? And therefore, it looks like this has an AR1, because why AR1? First of all, it is, the autocorrelation is decaying, right? And what about the partial correlation? In period 1, it has a big spike, and then these are like very small, right? So that tells me that is very typical of an AR1 process. And again, look at your ARMA modeling, Box-Jenkins type of modeling strategy, and that's where these are very standard things that we normally would teach, right? So again, looking at the Q statistics, looking at the autocorrelation, I suspect that there is arch effects. And then I also, so if you look at eViews actually has a built-in statistics, a built-in test for testing for autocorrelation, testing for arch effect in the residual. So I use that routine. Only thing you have to do, you have to choose the leg length. So I chose a leg length of 12. Generally, if it is monthly data, that is pretty standard that you pick a leg length of 12. So here, what I see is, first of all, many of these legs, particularly after leg 4, these leg length are not statistically significant, right? So it looks like I can actually reduce the leg length in this test. So irrespective of whether I do it, I did several persons. So again, these processes are, you cannot do it in one go. So you have to do a little bit of trial and error in order to figure out what is the appropriate test or what is the appropriate model, right? What is the appropriate test equation? Because here, yeah, it doesn't look like that leg 12 or 11, 10, these are important. So you can basically drop them, because there is a danger of including too many legs, right? So that eats up a lot of degrees of freedom. That means your estimates become very imprecise. And that's why you have to be very careful. And a parsimonious specification of model is always a challenging thing for any applied empirical economist. Because many a times, particularly when it comes to macroeconomic data, we have very limited data points. So here, so we can look at the F statistic, and this is actually an LM test statistic. So both basically reject the null of no arch. So here, the null is no arch. right? So so this also indicates that there is an arch effect. So here I did one more thing which I talked about before. You extract, so you create a new series which is essentially the squared the error term, and you regress that squared error term on its lag value. So that's what I did. I'm sorry, I had to like this blocking my view. Okay. So again, if you look at this simple equation, which is basically the squared residual, regressing squared residuals on its lag value, and here I'm doing one lag, right? So that one lag turns out to be very highly significant. In fact, if you look at the coefficient is 0.95. That means it's highly persistent, right, at one lag. And then I kind of increase it to 4 lag. Even second lag is important, third lag is important, fourth lag is important. The reason why I have done up to 4 lag or even more, here I want to point out something which is very important. First of all, see the second leg and the third leg, they are negative, right? They are negative. And when you include more than one leg, what happens? The coefficient for the first leg is greater than 1, which are violation of all the assumptions that we made, right? What assumption did we make? That the estimates or estimated coefficients should not be greater than 1, and they should not be negative. But here we have two estimates, two estimated coefficients which are negative, and one estimated coefficient which is higher than which has a value which is higher than 1. So that means this particular method, this is kind of a very rudimentary method of modeling arch. So you estimate the y equation, the mean equation using least square, and then extract the residuals, and then you estimate another regression using the squared value of the residual as the dependent variable on its lag value, right? So that is a way of doing it, but then that kind of could be problematic when it comes to satisfying all the assumptions that we make about about the model that we have talked about. Now, how do we do that then? So luckily, like, we can estimate both the model, both the equations, the conditional mean equation and conditional variance equation together using the maximum likelihood method. Okay. Of course, that likelihood function will depend on what kind of assumption we make about the error term, if it is, whether it is standard normal or student t or whatever distribution we assume, that will determine the likelihood function. But we can use the maximum likelihood method in order to simultaneously estimate both the conditional mean and conditional variance equation. So that's what we do now. Here I am estimating this conditional mean and conditional variance using the maximum likelihood method. So you can, in this, again, this is from the eViews output. So here in this first part, you see the conditional mean equation. So here is the coefficient for the constant and the trend. And this is the variance equation. And I am estimating an Arch1 model, okay? So going back to our ACF, right? So there was some indication that it probably is a AR1 model, meaning Arch1 model, or that will give us the best specification of the model, right? So, so there are a couple of things that you need to figure out. So for example, let me see if I can bring up that okay, here. So this is, so this is the window that you will see when you try to estimate. So only thing you have to do, you have to, so go to quick and go to estimate equation. You change the method. Generally, the default method is least square. So you go to Arch, right? So once you click on Arch, then it will ask you these questions. So what is the mean equation? So here I put log X rate, which is basically logarithmic value of the exchange rate, followed by a constant and a trend, right? So that's my basic model. Again, I am not trying to tell you that this is the exact or appropriate model. This is just an example, okay? So exchange rate may have a different appropriate model. I don't know, and I have not done that experiment or done that trial and error iterations that I need to do in order to appropriately model exchange rate. I have not done that. This is just an illustration example, okay? So let's say just by looking at the data, I thought that this might be kind of a more or less a good representation of the exchange rate. So that's how I did it. And then you have to specify the variance and distribution specification. So variance, of course, the default is Garch Arch, and there are some other stuff here. Of course, again, I will not have time to talk much about E-Garch, Parch. So E-Garch is basically exponential Garch, P-Arch is basically power arch or power Garch, and there is something called component Garch or component arch as well. So we are now kind of using the default one. And then here you have to specify the order. So I say that looking at the autocorrelation, it looks like it is arch 1. That means there is no Garch effect. There is no, so I will put it 0 here. And then it also kind of asks for threshold or order. So you will be using threshold order if you suspect some form of nonlinearity in the variance equation, conditional variance equation. But in this case, the default is 0. That means there is no nonlinearity. So let's kind of keep it like that. And then if you want, or if you suspect that there are some other variables, right, other than the lag value of the residuals, then obviously you can, that influence the variance, conditional variance, then you can include those here in variance regressors, right? And then what kind of assumption do we make about the error term? Well, here the default is normal, which is Gaussian distribution, right? But then you have other options as well, generalized error, GED with fixed parameters. So depending on the situation or based on your assessment of the error term, and there are different ways to look at how the error term looks like. So if you suspect that, well, the distribution should be something other than the normal distribution, so you can go ahead and choose from those options. And then do you want to put some restrictions? So there are two different types of restrictions E-views essentially allow you to do. One is IGERT, which is a short for integrated Garch, right? So integrated Garch meaning you basically force all the persistence parameter sum of the persistence parameter to be 1. So that's the Eigert's restriction. So you put restrictions on all those coefficients in the variance equation that you are going to estimate. And what is that, those restrictions? You force the sum of all these estimated coefficients to be equal to 1. So that if you do that, that will be Eigert. And then the second option it offers or it gives you is variance target. In that case, you basically let in the conditional variance equation, there is a constant term. So you put a restriction on that. You let that constant term to depend on the unconditional variance plus the estimated coefficients from the variance equation. Okay, so if you do that, that is basically the variance target. So we will kind of continue with none here, the simplest one. And then there are some options that you have to choose from. So there is this estimation option. So what kind of optimization method you use? Because when you use maximum likelihood, you also have to pick, because it will be an iterative process, so you have to pick the optimization method. So BFZS, I generally always forget the name of those guys who came up with this algorithm. So there are a couple of options here. I will stay with the default one. And then step method, well, default is actually Marquardt. So I will again stay with the default. Maximum iterations 500. You can increase it to 1,000, 5,000, whatever that is. Convergence is achieved when the difference gets smaller than 0.0001. I think that is pretty good. And then, so in order to estimate this AR, autoregressive coefficient, and MA, moving average coefficient in an Arch or Gertz model. Of course, in this particular example, I am not estimating MA, moving average coefficient, right? Because that is, I have set it to be 0. But in a more general form, which is called the generalized AR, generalized autoregressive conditional heteroskedasticity, there you also have to specify a moving average coefficient, right? So here, so in order to start this iteration, this estimation process, you have to initialize it. You have to basically start from some starting value, right? So this is this starting coefficient values. This is what it is asking for. So if you go with the default, which is EView supplied, they start from this estimated, initial estimated coefficient, and then they use some smoothing algorithm to kind of update that initial values, okay? And for updating, if you don't change this, they will use a parameter of 0.7. So 0.7 of the previous, and it goes kind of go back and go over and over again, right? So, but then you have different options. You have 0.9, 0.8. So you can choose any of those. Here, I think it's a reasonable one is 0.7. If you pick 1, then that means you are basically choosing the unconditional variance, okay? It automatically include a constant. And then what about the covariance method? So how do you estimate the covariance of the variance equation, right? So you can go for ordinary, in which case it will be done the way it is done in any regression estimate. If you use Volatility and Ulrich, that will basically kind of control for heteroskedasticity. Similarly, there is another way of doing that by the Hoover and White method. So yeah, these people basically try to correct for, these are kind of robust standard error estimation method. So they you can choose from them, okay? So let's say we go with Volatility and Ulrich, and then we kind of click it, and then these are the results that we get, right? And this is basically your variance equation that gives you an estimate of this conditional autoregressive heteroskedasticity, or you can say that conditional variance. So it will give you an estimate of the conditional variance. So that's how you would do an arch or GARCH model. Okay, let me go back to my, again, I don't have much time. So let me kind of try to wrap up as quickly as I can. I don't know why I have to. Now, there are some shortcomings of the typical arch model. So if P is large, that lag in the arch is very large, then the problem is it takes away a lot of degrees of freedom. So as a result, the coefficients are estimated imprecisely. And moreover, as you have seen, more often than not, you will find that there are coefficient estimates which are negative, or coefficient estimates which could be greater than 1. As a result, you have to put a lot of restrictions on a lot of coefficients, right? And that could be very restrictive. So if you put a lot of restrictions, right, so coefficient restrictions, then obviously it's not fun. It's not, it becomes very restrictive. And sometimes if you find negative coefficient, it is very difficult to interpret those coefficients. What does they basically tell you? And that's where Bolarsev, he came up with this idea, or at least extended this arch framework to include a moving average component, which he calls the generalized autoregressive conditional heteroskedasticity. So what happens when you extend arch to GARCH, you not only include, so if you look at this slide here, so here you will find that so this is already, was already there. No, I'm sorry. This was already there in the arch specification. So in arch specification, essentially you have this. So in addition, you include a lag value of the variance, right? And so it becomes, so it is an extended conditional variance equation. So here, again, we assume that all coefficients are positive, and delta 1 and theta 1, they are all less than 1. Otherwise, again, it will lead to a very explosive behavior of the variance, which is not desirable, right? It has to be, they have to be positive. Otherwise, again, variance cannot be positive, okay? And from experience, so even if you read the literature, read many of the applications of arch and GARCH, you will find that GARCH 1.1 actually does a very good job, okay? So you can generalize GARCH, you can include more lags, right? You can include both AR terms and MA terms, but then generally GARCH 1.1 is a very good representation of volatility clustering, right? And you can actually replace a very high order arch. Let's say P is 12 or P is 24, right? So that kind of very high order arch, you can very conveniently model or remodel or parsimoniously remodel as a Garch 1-1 model. So Garch 1-1 is a very popular model in that sense. Okay, so here what I have done, again, I'm going back to my example of the exchange rate between US dollar and Indian rupee, and I basically estimated a Garch 1-1 model. Here again, thinking in terms of the E-views, there you have to pick. In fact, default is 1-1, therefore you don't have to change the Garch term. And here, by looking at the Garch term, as you can see, that the Garch term is not statistically significant. Again, that kind of tells me that my initial suspicion that probably this exchange rate conditional variance can be modeled as a Arch 1 model has been reinforced or has been supported, because here Garch term is not significant. So it can be generalized to Garch PQ, so you can include more legs of the estimated residual and the variance. So this will be a very general specification of the Garch model. Now, before I conclude, because I think I'll have to leave anyway. So before I conclude, so let me kind of quickly go over a few additional things. So there is also an option that you can include this risk factor in the mean equation. So this risk factor, you can say that influence your mean as well. And when you do that, that is called the Garch in mean model. And in E-views, there is an option. If you look at the first window on the right-hand side, there is an option. So if you don't choose that, then it is basically says none. But then you can, from a drop-down menu, you can actually pick the Garch factor, which is conditional variance. You can include conditional variance in the mean equation. Integrated Garch, of course, you drop the constant term and you make the sum of all the estimated coefficients of the Arch and Garch coefficients equal to 1. So that's an integrated Garch model. Okay, so you are putting a very specific kind of restriction in estimating the Garch model. Then there could be threshold Garch or torch, you call it torch, where you suspect that there could be a non-linearity in variance. Let's say volatility respond differently when there are bad news versus volatility respond differently when there is good news, right? Or there is, it responds differently when there are negative shocks versus it responds differently when there are positive shocks. So in the financial market or in the macroeconomy, there are always good news and bad news, particularly in the financial market, right? So when you suspect that variance respond differently to good news and bad news, then you can go for torch model. So let me kind of stop here because, again, as I said, I apologize. I'll have to leave a little early because I have another meeting, an important one. But then, so I hope I have been able to give you the very basic, the concept of arch or arch effect and how we can go about modeling it. Of course, it would have been ideal if I could have taken an example for each of these different things and then could have shown how we do that. But in general, I think I have covered the very basic. And again, just remember that we are storytellers, and in order to tell good stories, we have to use good methods. And these methods are, it is very difficult because theory is something else. In fact, sometimes I envy those people who work on econometric theory or statistical theory. For them, everything is nice and beautiful, right? It's very exciting, and they can always generate simulated data, and they can kind of tell us whatever they want to tell us. But then when it comes to applying those theories or those theoretical methods to actual data, it is always kind of very, very difficult unless you acquire some sort of a skill over time through repeated application to different data set, and you have a good sense of data. You basically don't become a perfect empirical economist or social scientist, I would say. And it comes with practice. It's not that you will ask me, okay, what is this? If you ask me a very simple, okay, so how do I do this or what do I do that? My initial reaction would be, I don't know. But then there are certain things where we face the same problem, and I have probably faced the same problem, and there I can kind of provide you some useful information. We can share some useful information. But in general, I think it is about practicing. It is about kind of, so many of you probably have read this. There is a famous article by Salai Martin at Columbia University. So he published a paper, if I remember correctly, in QZE, Quarterly Journal of Economics. I just ran million regressions, or something like that. It's a very fancy title of the paper. But the point was that, yeah, you have to run million regression before you get what is appropriate for modeling particular phenomenon that you are trying to study. So with that, I wish you good luck and best wishes. Let me see if I can write my email address so that you can, let me write it in the chat box. This is my email. So eco for economics _HKN Hiranyakumarnath at shsu.edu. So if you have any question or which I have not covered, or because of lack of time, I will not be able to respond now, please email me. I'll be happy to respond to your email. I'm sorry, I have not sent it. I wrote it, but I have not sent it, and that's why you cannot see it. So eco _HKN at shsu.edu. Okay. So sometimes what happens, if it comes from unknown, nowadays they put a lot of firewalls. So if it comes from an unknown email, it goes to the junk email box, and I check them, but then not very regularly. So be patient, and if I don't respond immediately, just give me some time. I will, and then don't hesitate to kind of resend it, because I'm fine with like repeatedly bugging me, because that should be the nature of a good learner. And thank you very much. It's very nice meeting you. Wish I could meet you in person.
My vote of thanks to today's speaker of the second session, Professor Hiranyakanath Sir, Professor of Economics and International Business at Sam Houston State University, USA. We are very much thankful, sir, for your kind cooperation and giving a valuable time, and also to share your knowledge with the participants. And we are indeed have also learned a lot from the session. And as a learner like me, it will truly help in my research work. And I would like to express my gratitude to Professor Hiranyakanath sir for your valuable and novel lesson. And truly, it was an honor for us to participate, to learn and listen from such an experienced and great professor, and take invaluable input that will enrich our research experience. So his emphasis on variance, volatility, clustering with examples and data from 2012 to 2022, and highlighted variance model such as autoregressive conditional heteroskedasticity, which deals with time series, and also sir has thrown lights on several ways to detect the arch effect and how to test the arch effect, and also explain the Gurch and Turch model. And also my vote of thanks to conveners, Dr. Dipjyoti Chaudhary sir, joint convener, Dr. Shrabanti ma'am, Dr. Taratnath Sahu sir for organizing such an informative program. And I also extend my gratitude to all the coordinators for their continuous help to conduct the program smoothly. I also take the opportunity to thank all the participants without whom the program would not be possible to conduct. Thank you once again. Thank you.
Thank you so much. Thank you to everyone. And you have a wonderful evening and a good night.
You have a wonderful day, sir. We hope one day we will meet in the real world instead of virtual world. Thank you so much, sir.
I'm hoping to see you in person very soon.
Yes, sir. Yes, sir. Even I am trying to do that.
Yeah.
Thank you,
Thank you
sir.
so much, Shravanti, for everything.
Thank you so much, sir. Always give my side. When I request, you never say no. You always try to be my side. Thank you so much.
Thanks. Thank you. Good night.